Okay, so today we keep talking about network security. We are moving to the application layer today. So at the application layer, we have all kinds of protocols built on top of TCP, IP. Some of the protocols we do not some of the protocols on this slide, we do not use them very often, or we basically stop using them. Like, I don't know who is still using FTP or Telnet, but some of the protocols we still use every day, like HTTP, HTTPS, DNS, and there are just many different application level protocols coming out every day. Everyone can design their own application level protocol. Today, we will look at a specific protocol, DNS, and then we will feel what are the security needs DNS has, and why DNS or any other application level protocol, they have security issues. So we have this DNS, which is domain name system protocol, and we use them to there is a mapping between a domain name and IP address. And usually we do not remember IP addresses. However, it's easier for us to remember domain names. So when you use your browser, you usually do not type IP addresses. You just type domain names. So a little bit of history about DNS. So the ARPANET they used to use, which is ARPANET eventually becomes our internet. Then they use a centralized file called hosts.txt, and in that file that contains the mapping between names to addresses. At that time, that address do not necessarily is IP address, which is not IP address, because at that time we don't really have IP protocol, but that is some kind of network layer address that can be used to identify hosts. Then that time, administrators, they just exchange emails to update that hosts list, and that they share the hosts list, that host.txt file, in FTP servers for others to download. The problem with this approach is scalability, right? There could be multiple different versions of hosts on different systems. And whenever you want to transfer them, you transfer the whole file. And also, because there are multiple versions, there could be name collisions. So back in the 80s, Paul Malker-Petris, basically, he released the first version of DNS. Then people started working on this to eventually develop the DNS like what is today. So before talking about DNS, let's look at another concept called Uniform Resource Identifier, URI. So URI basically can identify a resource on the internet. To identify a resource on the internet, it has more information than the domain name, than the host. So usually we can have this is the syntax for a URI. The URI starts with a scheme, which the protocol you want to use to retrieve this resource. It could be the scheme here could be HTTP, could be FTP, or any other protocols, even mail2, that could be a scheme, right? So if you use a browser, the browser will use HTTP or HTTPS as the default scheme. So when you're in the browser location address bar, when you type something, you type a domain name, you type a URL, you do not necessarily have to type HTTP or HTTPS because that's implied, okay? But you need to know that there is a scheme there. Then after that, there could be a username and password. if there is authentication before accessing that resource. So after that, there is a host name. The host name can either be a domain name or IP address. So if you look at the 5 examples here, the HTTP one, the domain name is 3w.ietf.org. Then the mail2 example, the domain name is example.com. News, there's another domain name which has actually 5 or 6 parts. So that part is a domain name. So after the domain name, there will be a slash, which tells the remote server, the host, on that host, where is the resource on that host? So this is basically the path part. So after the path, there could be some queries, also could be some fragment. But the most important here is all of those parts, they are optional. The host part is not optional. If you don't even know who is the host you are talking to, then you are not addressing anyone on the internet. Other part, for example, path, could be the root path if you do not give anything. The port number, if you do not give a port number, then the default port number for that scheme will be used. Like HTTP, we will use 80. FTP is 23 or something. I don't remember what's the port number for FTP anymore because no one is using that anymore. So the domain name system is a globally distributed, scalable, and reliable database. It has 3 major components: a namespace. There are servers making the namespace available, and resolvers, clients, which queries those servers about the namespace. So there are just if not billions, then hundreds of millions domain names available right now. There are a lot of companies actually, their business model is just to sell domain names. DNS try to solve many problems. One of them, the problem is scalability. What we want to have is a huge database of mapping of domain names to network addresses, and there's no limit to the size. There is no limit to the number of queries because everyone uses DNS protocol many times a day. Thousands or even billions of queries should be handled easily in a very short time. And the queries actually are distributed among masters, slaves, and caches, which we will say later. To achieve reliability, in DNS, data is actually replicated. Data from master is copied into multiple slaves, and the clients, they can query the master server, and they can also query slave servers. And usually, clients, they will first query their local cache. And the DNS protocol itself can use either TCP or UDP. So UDP, the advantage is it's fast, it's very cheap in terms of package size, transmission cost. TCP provides a more reliable transmission, but for DNS, sometimes maybe it's not necessary. Then the namespace is a structure of a DNS database. It's basically a tree structure. The root node is on the top, and each node has a label. The root node doesn't really have a label, then just a double quote. Then we have top level node, second level node, third level node. This is similar to our telephoning systems. The root node can be just the plus. Then we have a country code, like US is 1. Other countries have a different country node. Then the second level, we have the regional code, like 716, something like that. So there are some rules for this tree structure. First is each node must has a label. The root technically doesn't have a label. Then each node, every other node have a label, and a label is a string up to 63 bytes, and also the label can only have English letters, and also the dash or hyphen. That's the only allowed characters in the host name. That's why you do not say the host name with a percentage sign, with a dollar sign. You have never seen a domain name like that, because that's not allowed right now. In the future, who knows? Maybe things will change. And also, sibling nodes, they cannot share the same label. For example, at this level, you cannot have two fools. Then, because this is supposed to be a unique, globally identifiable identifier. If they have the same, then you cannot tear them apart. Also, you cannot have this and sign here, like a AT&T. You cannot have this and sign. So a domain name is the sequence of labels from a node to the root. Because usually when we have a domain name, we read it from left to right, right? So the leftmost actually maps to a node, like a leaf node. Eventually we map to the root, which is empty. They are separated by dot. So for example, the root node is nothing. The first level node, we have com, edu, gov, military, net, those kind of things. Then under those companies, then we have different companies' names. Under edu, we have different university names. So when we read them, we read from the leaf, then to the root node. So for example, this one would be berkeley.edu, right? So that will be a domain name. Berkeley.edu will be a domain name. So the top level domain name, which is at the edugov.com level, there are, I don't know how many are there right now. I think it's more than 1,000 at least. So this slide I made several years ago. At that time, there were actually 700 top-level domain names. So yeah, familiar with .com, .gov, but there are actually many more than that. I have seen recent years, we have seen top-level domain name is someone's last name. So a lot of people with the same last name, they just said we want to have a domain name with our last name. Then the ISOC approved that. So I think at least there was a career name Kim or Tim. Yeah, it's a top-level domain name. And also countries. Every country, they can have their top-level domain name, .us, .cn, those kind of things. So I don't know how many are there right now. Definitely more than 1,000 top-level domain names right now. That's a little bit surprising because usually we are only dealing with .com, .gov, and we thought there are probably just 100 of them, but actually there are more than 1,000 right now. Then one domain can be a subdomain of another if the domain name ends in the other domain's name. For example, CSE, the computer science department, .ub.edu is obviously a subdomain of ub.edu and also a subdomain of edu. And the ub.edu is also a subdomain of edu. Administrators, they can create subdomains to group hosts. So a host here could just be a computer. And an administrator of a domain can delegate the responsibilities for managing a subdomain to someone else. The parent domain retains links to the delegated subdomains. For example, when you visit ub.edu on your browser, it probably actually redirected to 3w.ub.edu, which could be one host or many hosts to serve UB's website. Then if you visit csee.eb.edu, then you visit the website of the CSE department. Then inside the CSE department, we can have more hosts, some servers, and they will have their own name, then .cse.ub.edu, right? So the left-hand side of the domain name is actually the host. The right-hand side is a bigger domain. So from left to right, you go from a particular host to a bigger domain name. So each time an administrator delegates a subdomain, a new unit of administration is created. The subdomain and its parent domain can now be administrated independently. So those units are called zones. So delegation is a key to scalability in DNS. So name servers, they store information about the namespace in units called zones. The name servers that load a complete zone is said to have authority of that row. So usually more than one name server are authoritative for the same row. So this ensures redundancy and spread load the workload. Also, a single name server may be authoritative for many different zones. For example, here we have two zones. One is ISA.org. That's one organization. Then there's another company, nomimum.com. That's a company. And there could be some name servers in charge of the mapping between inside those zones. The type of name servers, mainly two types. Authoritative, they maintain data. There are master name servers where data can be added. And there are slave name servers where they just retrieve data from the master servers. Also, there could be caching. They store data obtained from authoritative servers. The root servers, the root zone files lists the names and IP addresses of the authoritative DNS servers for the top level domains, like .com, .gov domains. The root zone file is published on certain servers. They are named from A to M in the internet. So root name servers operations are currently provided by volunteers. So here is the list of the 13 root servers in our internet. So those are the root name authorities. You can say they're managed by, some of them managed by companies, some of them managed by universities or US government. Some of them are non-profit organizations, like ICANN here. Some of these are VeriSign, then DoD, US Army, NASA, Maryland, USC. So those are the 13 root servers. So let's take a look how this works when you want to visit a website. When you want to find out the IP address of a domain name, how does everything work? Let's say we have a workstation. The workstation has its own domain name. We call this workstation Annie. So Annie is part of the organization West, or the Group West. And the Group West is part of a company called SP Rockets. And it's a company, so it's a .com. Then inside this company, there is a local name server called Dakota, which is another host in the same network. So Dakota is part of West and part of sprocket.com as well. So Annie here wants to visit a new URL or a domain name, which is 3w.example.com. Then Annie will ask Dakota, what is the IP address of this? So this is a very similar behavior you have seen at other layers of computer network. Data link layer, IP layer, you'll see similar things to get the mapping between two different network addresses. So here we just want to get the mapping between URL or domain name to IP address. Then Dakota in this case doesn't really know the IP address of 3w.example.com. But Dakota knows this URL top level domain name is .com. So, well, it actually, right at this point, it doesn't know that. Then it will ask one of the root servers. Like we said, we have 13 root servers. Somehow it knows the root server's IP address, then it directly asks the root server, so what is the IP address of 3w.example.com? Then the root server will say that, I don't really know the IP address of that, but I know that this domain name belongs to .com. And I know who is the name server for .com. Then it will basically refer Dakota to the .com root server, name server, which in this case is the f.gtld, which is global top level domain name server.net. Then Dakota will ask this server, what is example.com? Then this server will say, I don't really know, but I know a lot of other name servers, and they may know who is example.com. Return that list to Dakota. Then Dakota will try to contact those name servers. And eventually, one of the name server, for example, ns1.sanjose. Will say, hey, I know the IP address, and give that to Dakota. Then eventually, Dakota will return that to Annie. So Annie, this host, will be able to talk to 3w.example.com. So that is how it works. Of course, not every time, excuse me, not every time you try to find an IP address for domain name, you will go through all the process, because there are a lot of caching in between, right? Even your local system, they may cache this DNS to IP address mapping. So in the domain name system, there are also three concepts: registries, registrars, and registrants. So I assume some of you bought domain names before, right? Through GoDaddy.com, names.com. You probably bought your own domain name, try to set up website. So you know those rules, right? So registry is just the namespace database. The organization which has edit control of that database. The organization which runs the name servers for that namespace. Registrar is the agent which submits change request to the registry on behalf of the registrant. The registrant is the entity which make use of a domain name. So when you purchase a domain name from GoDaddy.com, then you are the registrant. You can buy a domain name from GoDaddy.com. So when you purchase a domain name, the registrar, basically, like GoDaddy, will share that information to registry and eventually that information will be distributed to distributed databases, and those master and slave namespace servers will update the record. So whoever on the internet get your URL will be able to visit your website. So the DNS protocol, how does that work? So DNS primarily uses the UDP protocol on the port number 53. Used to, when the old port numbers are used for UDP protocols, the even numbers are for TCP protocols, like HTTP use 80 port 80 or 8080. UDP use DNS on UDP will use 53. The DNS requests consists of just one single UDP request, followed by a single UDP reply from the server. So very simple, doesn't really cost much. And the DNS protocol use two types of messages, just query and reply. And they have the same format. Each message consists of an application level header, the DNS header. Obviously, before that, we have a UDP header. Before that, we have IP header, then Ethernet header, or whatever network layer headers. Then it also have 4 sections in that packet. We have question, answer, authority, and also additional space. A header field controls the content of those 4 sections. So this is what a DNS header looks like. We have 2 bytes identifier, 2 bytes flags and codes, question count, answer record count, name server count, additional record number, something like that. Then the flags look like this. There's operation code to tell what is this request, and also response code. So this is obviously application level protocol, relies on UDP, but like many other application level protocols, obviously you can also use TCP for this. But the application level message is so short, so it doesn't really make sense to use a very heavy underlying protocol like TCP. UDP would be enough. In this header, some of the fields, we can take a closer look at it. There is one bit called QR, query or response flag. So if the message is query, we clear this bit. If this message is a response, we set this bit. That's it. So just one bit, we can tell this is it's a request or a response. Then the opcode field tells receiving machine the intent of this message. 0 means normal query. There could be other options like reverse query, server status, just to check the remote server's status. There is authoritative answer. Set this only when the responding machine is the authoritative name server of the queried domain. Note that this is just a UDP protocol. Everything on this can be modified, can be tampered, right? So basically, whoever set this, they're claiming they are the authoritative name server. This protocol itself, so far, there's no security verification. There's no message authentication. There is no integrity check. Then there is also a truncate field if the packet is larger than the UDP maximum. Maybe, for example, the number of authority returned record is too many. There are too many records. One UDP packet cannot contain it all. Then we need to set this. Also, recursion desired bit. If 0, it means the query is a iterative query. If 1, this is a recursive query. So recursive query means the resolver must complete the recursion, and the response must be either an IP address or an error. So a host OS usually send a recursive query to a DNS resolver. Let's say 8.8.8.8. That is a DNS server maintained by, I believe, by Google. So Google chose a very easy to remember IP address. So if your local DNS server is not working, then you can just use this IP address as a DNS. And it's easy to remember. Then let's say a host server, they can send a recursive query to the resolver. Then resolver should either give an IP address for whatever domain name you're asking, or just give an error. Okay. So let's say we have Google's DNS server here. The host is asking what is the IP address for 3w.example.com. Then the Google DNS server will ask all those servers we showed before to figure it out and tell the host what the IP address is. On the other hand, the iterative query means the response must be an IP address, the name, the location of an authoritative name server, or an error, which means when the Google's DNS server, or the previous example we showed that, tries to ask what is the IP address for 3w.example.com, it should send this iterative query because the servers this server try to talk to, they don't really directly have the IP address for the domain name you're asking, and they are not going to find out that for you. They only want to refer you to other naming servers. So they're to make their job much easier, to make their throughput much higher. So they're not going to do the recursive queries for you. So your DNS server is actually using this type of DNS messaging to talk to other DNS servers. Also, the 9-bit 9 in a response can tell the host if I have the ability to recursively answer your queries. Basically means if I'm going to ask other servers until eventually I find out the IP address. Or I will just give you a list of name servers I refer you to. Also, there are some reserved bits, obviously. Also, the return code have 0 means no error. Maybe I will find the IP address for you. Or there will be 3 means the name doesn't exist. So the remaining 4 header fields are the number of questions, answer resource records, authority resource records, and additional resource records. These numbers vary depending on whether it's a query or response and what kind of response it is. In general, there will always be at least 1 question there. Then there will be some answers. So this is one example. So one host trying to ask what is the IP address for 3w.google.com. And this is a screenshot from just Wireshark. And in Wireshark, you can see the whole data package from the Ethernet layer to IP layer to UDP layer and eventually to the application layer. And the application layer, Wireshark will know this is a query, and this is a type A class inquiry, and is asking what is the IP address for this domain name. Then this is a corresponding answer, and you can say it will give not only one answer, many answers. It will say 3w.google.com has this IP address, this 1.4. Actually, there are many IP addresses that map to this domain name, 3w.google.com. So it returns many of them to the host. Then the host eventually will choose one. Because the IP package, you can only use one destination IP address, right? You cannot use multiple. So the host eventually choose one to use. For authority resource record, let's say, so the type here will be not type A anymore. The type here will be NS, which is a name service, name server, right? So here we are. So you can see here, this one, it's not really giving the google.com's IP address. Instead, it gives the name server's URL, which is nameserver2.google.com, or there are several other name servers. Then to recursive queries, you can ask them what is the IP address. But those are the name servers domain name. And maybe even to get those name servers IP address, you need to ask other DNS servers or what is their IP address. So cache, obviously, let's say the name server here wants to respond to the host with the example.com's address, but it can cache that mapping locally. It doesn't have to send out the messages to all the servers there. So the DNS protocol actually has a field which is time to leave. This is very similar to the IP package. So in IP package, you also have a time to leave field, TTL. So that field determines how many routers should forward this message until one decide to drop this message. This TTL means for the data I give you, you can save it for how many days and as a caching, and you give this information to all the hosts who ask for the information. So one attack here obviously is the DNS cache poisoning attack. You can spoof the DNS records and set a very long TTL time. So the server will remember that wrong mapping for a very long time, and all the machines that ask the DNS server to give the IP address will give the wrong IP address. So how does this work? Let's say we have an attacker. The attacker will send out a spoofed DNS response. The DNS message itself is not, there's no, well, first of all, there's no encryption. And there's no point to encrypt, right? Because the confidentiality here is not the goal. The DNS servers, they want to advertise the mapping between domain names and IP. Confidentiality is not the goal. But integrity is important here. Attackers should not be able to change that. So attackers can send out spoofed DNS message to DNS servers or to host directly, and the host or DNS servers may cache that. One way to solve this, obviously, we can use something like TLS, SSL. So HTTP we are using is basically based on TLS, transport layer security. So it includes encryption, it includes integrity check, everything. But the problem here is it's providing a lot of services we don't really need for DNS protocol. So when you visit a website, you want to use HTTPS, which is basically TLS. You want to use that because when you visit, let's say Facebook, you don't want anyone on internet or anyone on your local network to know what your communication with Facebook, because those posts, whatever, they could be private. Also, if you log in your BOA to transfer money, if that's not encrypted, if that's not authenticated, then anyone will be able to do that, right? However, for DNS, there's no need to encrypt the message. So we don't want to use TLS. It's too expensive. That's why we have a new protocol called DNSSEC, Domain Name System Security Extension. This is tailor-made for DNS. This is a suite of extensions that add security to DNS protocol by only enabling DNS responses to be validated, to be authenticated. That's the only goal, the integrity and authenticity. So DNSSEC provides origin authority, data integrity, and authenticated denial of existence service. So with this DNSSEC, DNS protocol is much less susceptible to all kinds of spoofing attacks. So like all other security protocols, we use crypto to solve this problem. And when we think about data integrity and authenticity, we usually think about a public key system, right? So we use public key algorithm, especially signatures. Signatures are applied over the DNS data. Then by comparing the signatures, so whoever issues that DNS response, they have to sign using their private key. So whoever gets this response, they can verify using the public key. So the integrity, both integrity and authenticity of the data can be established. So basically, the solution of many of the problems we have seen in the later half of this class were actually presented to you at the beginning 2 weeks of this class. Just use those crypto solutions. Many of the security solutions we use are just those crypto solutions. So in this solution, the private keys obviously will be kept private, stored locally, and the public keys can directly publish in the DNS protocol the message as the DSN key resource record. So previously, there were additional record fields, right? So we just put the keys there. Then the signatures will also be put in the additional resource records. So this actually has been very convenient. It can be backward compatible. So to validate the public keys, we also distributing keys through DNS. There is one trusted key to establish the authenticity of other keys. That's basically the root key. Then build the chain of trust from the root down. Then all the parents, they need to verify, they need to sign the keys of their children. So this is the same. Actually, this is I think I showed you an example at the very beginning of the class when we're talking about public key. I showed you the UB website. When you click that little lock in the address bar on your browser, that gives you the certificate of that website, right? And it shows you who signed that certificate. Eventually there will be some root of trust which are installed on your computer. So your computer will only trust those kind of website. So this is very similar. This is basically the same technique. But that one is on top of TLS. This one is not really TLS, because this one we don't care about the confidentiality. Okay, that's basically all I have today for the application level security and DNS security. Any questions for today? Okay, if no questions, then see you guys this Wednesday. We will talk about intrusion detection systems.